Hey, so my name is Annika, and this is Chapter 5 of Physics, Work and Energy. So in this chapter, we're going to be covering a few main topics. We have work, energy, the conservation of energy, and power. Let's take a look at these concepts. We'll start with work. Work is done when a force causes displacement for an object. In other words, a force causes an object to move. Therefore, we define work as force times displacement, or in other words, the amount of force applied to the object times the amount that the object is displaced from its original position. So work is not done on an object unless the force causes the object to move a certain distance. That's because work also involves the displacement of an object. So for instance, in this situation, we have both a force acting on an object and an overall distance that it travels. Therefore, work is done. However, when work is done on an object, only components of the force that are parallel to this displacement do work. So in this second situation, where we have a force that's acting at an angle, only the horizontal component of the force does work, because only that component is parallel to the displacement. Because we're looking for the component of force that's parallel to displacement, we're going to add on to this equation a little bit. We'll rewrite it as work equals force times displacement times the cosine of the angle between the force and the horizontal. Let's take a look at a few examples. Here with this red block, we have a force that's pushing the block up at an angle. We'll call that angle theta. Now, we only want to look at the component of the force that's parallel to the displacement, or this horizontal component. Therefore, we'll define work as force times displacement times cosine of theta. That will allow us to solve for the horizontal component. Now we'll look at two special cases. In this first one, the force is applied in a vertical direction. In the second one, the force is horizontal. We have the same force and the same displacement in both cases, but the work is different. Let's write out the equation. In this first situation, work is equal to a force, so 2 newtons, displacement is 3 meters, and cosine, we'll call theta 90 degrees, because that's the angle between the force and the horizontal, 90 degrees. Now, cosine of 90 degrees is 0, which means that the overall work performed is 0. In the second situation, where that same force is applied horizontally, we'll write work as 2 times 3 times cosine of 0 degrees. Cosine of 0 degrees, as we know, is 1. So this now becomes 1 times 6, or 6. Now let's look at the dimensions of work. So we've already defined work as force times displacement, or in other words, force times a certain distance that's been traveled. So if we're writing the units, or dimensions, for this work, we know force is measured in newtons and distance in meters. Therefore, we've defined the unit for work as the joule, expressed as a capital J here. 1 joule is equal to 1 newton meter. So the units of joules are newtons times meters. Work also has a direction. It can be either positive or negative. Positive work is work that acts in the same direction as the object's displacement. For example, here we have this displacement that's going over here, and the force is going in the same direction. Therefore, the work is positive, and it's causing the object to accelerate. On the other hand, negative work is work that acts in the opposite direction of displacement. Here we have an object that's still moving this way. However, in this case, the force is pushing backwards. This would cause the object to slow down, or perhaps eventually turn around and start moving in the other direction. Now let's try some practice problems. Number 1. A tugboat pulls a ship with a constant horizontal force of 5,000 newtons over a distance of 3 kilometers. How much work is done on the ship? So first we have to be careful with our units here. If we have a distance of 3 kilometers, we need to redefine that to be in meters. So we know we have 3 kilometers, and that there are 1,000 meters in a kilometer. Therefore, the ship is traveling 3,000 meters. Now we can move on to solve the problem. We know that work equals force times distance. We know that the force is 5,000 newtons, and the distance is 3,000 meters. We can multiply these out to get that the work done is 15 million joules. Practice number 2. A shopper pulls a cart with a force of 35 newtons at an angle of 25 degrees above the horizontal. How much work does the shopper do on the cart over an aisle that is 50 meters long? So let's look at our equation for work again. This time, since we have a force that's acting at an angle, we have to include the entire equation. Work equals force, displacement, cosine theta. So now let's plug in the numbers we have. We know the force, that's 35 newtons. We know that the displacement is 50 meters. And we know that the angle is 25 degrees. Now we can plug this all in and solve to get that the work acting on the cart is 1,586 joules. Practice 3. If a neighbor pushes a lawnmower 4 times as far as you do, but exerts only half the force, which of you does more work, and by how much? So here we have your work on the lawnmower in this first situation. We see that you push down with a force F and a distance d. So your work is equal to force times distance. Now over here we have the neighbor's lawnmower. The neighbor uses a force of F over 2, but over a distance of 4d. If we multiply this out, we can get that the neighbor's work is equal to 2 force times distance. Therefore, the neighbor does more work than you do by twice as much. Number 4. A force F of strength 20 newtons acts on an object of mass 3 kilograms as it moves a distance of 4 meters. If F is perpendicular to the displacement, how much work does it do? So I've drawn out a diagram here, but you can probably see that a key word in this situation is perpendicular. We know that if a force is perpendicular to the displacement, we can call that an angle of 90 degrees. We'll draw it out here, 90 degrees. You might already have an idea of what the answer will be, but I'll write out the equation just to make sure. If work equals force times displacement times cosine theta, we know that the force is 20 newtons, the displacement is 4 meters, and the angle is 90 degrees. We can see that the cosine of 90 degrees is 0. Therefore, no work is performed on the object. And this should be pretty self-explanatory because we have already discussed that if a force is acting with some component that's perpendicular to the displacement, that component does not count toward the work that the force does.